Right. So now further use of this characterization of the dot product, the formula we have in the box here isn't particularly different than what we saw before. This is really just u dot v, which is divided by the magnitudes of u and v to solve for cosine of theta on the right-hand side. So it's essentially the same formula as the previous page, but it's just one step closer to being able to use this a little bit faster. So now if we're interested in finding the angle between two vectors, as the example is calling for, we've got vectors u and v here perhaps, we can use this formula right away and come up with what we need. This is pretty direct. We take the dot product of each of those two vectors. We'll get a number up top. We'll take the magnitude of each of the two vectors, divide by their product down below. And ultimately, we have root 9 in the denominator, root 98 in the denominator. That's 3 times root 98. And root 98 simplifies to 7 root 2. Ultimately, we have cosine theta is equal to 8 over 21 root 2. Now, solving for theta, we just take cosine inverse of both sides. And we arrive at this answer here. This is exact, so it's preferred. If a problem ever asks for expressing this answer in degrees to a certain number of decimal places, just make sure your calculator's in degrees, or radians to a certain number of decimal places, make sure your calculator's in radians. If the problem doesn't specify, you should be able to get away with something like this. Okay. Next up, the dot product for perpendicular vectors. Okay, so we just saw over here in this page that cosine theta is equal to this. Now, if the vectors u and v are perpendicular to each other, it means that the angle theta between them is pi over 2 or 90 degrees. Now, if that's the case, cosine of 90 degrees or cosine of pi over 2 is 0, which means that, well, if we have a 0 on the right-hand side, we have to have a 0 on the left-hand side. Now, the only way that we could be 0 on the left-hand side is if the dot product of u and v, the numerator, is 0. So that's a really good use of the dot product. If u dot v equals 0, then u and v are perpendicular vectors. Another word we use for perpendicular will be orthogonal. Okay, perpendicular and orthogonal are essentially the same things in 2 dimensions. Later on, we'll say orthogonal for higher dimensions. It's a more general term. So here we see the argument I just made. U dot v is u, magnitude v, cosine pi over 2, and that's, well, of course, 0 because cosine of pi over 2 is 0. So, and that's the converse. If we know that u and v are perpendicular to each other, then we'll know that their dot product must be 0. Okay, now we're going to have to answer the question of parallel in just a moment. We'll see that in the problem. So let's just get started with the problem. We're given two vectors, u and v, and they're expressed in terms of the standard basis vectors. No problem, we know how to handle that. And we're asked to determine whether or not they're orthogonal, parallel, or neither. So we don't have the check for parallel yet, but we would know this much. If two angles are parallel, then the angle between them is either 0 or 180, right? So we'll say that vectors are parallel if they point in opposite directions as well. So they're aligned with each other, but maybe going opposite directions. Now, that's the case when the angle between them is 0, or when the angle between them is 180 degrees, or pi. Okay, so if that's the case, and I've just done it for 0 here, then noting that they're parallel when theta is 0, then u dot v, according to our rule before, is equal to magnitude u times magnitude v times cosine 0. Cosine 0 is 1, so then we could simplify that to u dot v is equal to the product of the magnitudes. So that's your test for parallel. A little bit more work than perpendicular, but not too much, right? Now the other way is that if 180 degrees, if the vectors are pointing apart by 180 degrees, well, the only difference here will be that this will be negative. So if that's the case, then plus or minus the magnitudes times each other equals the dot product, then we'll always know that they are parallel to each other. Different definitions for different textbooks might say that parallels only if they point in the same direction as well. Okay, so for our given example, we're going to need some things to calculate this, but we have our test. It's right here. I'll leave it highlighted so we can refer to it. Now we've got magnitude of u is root 6 after we calculate it. Magnitude v is root 6. Very good. U dot v comes out to 5. Now, the magnitude of u times the magnitude of v is 6. Okay, these two things are supposed to be equal. They're not. One's 5, one's 6. So we know that these two vectors are not parallel. They're not even off by a minus sign. If they're off by a minus sign, then by some definitions, yeah, we'd say they're parallel. So we conclude that they're not parallel based on this. And that takes care of that consideration. Now, perpendicular. Well, perpendicular is the easier check. In other words, all we have to look for is whether or not the dot product is 0. Well, in this case, we've already calculated the dot product u dot v. We found that it was 5. 5 is not 0, so u and v aren't perpendicular either. Therefore, u and v are neither perpendicular nor parallel. So that's it for this type of problem. The order doesn't matter. You could check perpendicular first, then parallel. Either way, it might be better to go first with perpendicular, because if they are perpendicular, it's shorter work and you're done faster. But otherwise, it doesn't really matter. So vector projections. We have vector projection and scalar projection. So scalar projection is essentially it's the magnitude of a vector pointing in another vector's direction. So how much of a vector's magnitude aligns with another vector? Or in other words, if we were to draw the projection vector onto another vector, of one vector onto another, what is the length of that? Okay, and that's denoted by this comp of v onto u. So the scalar projection of v onto u. Notice how this notation is set up. V onto u, and we use this calculation right here. The vector projection of v onto u, this calculates the projection of v onto u, quite literally, and this result is a vector. The previous result was a scalar, but the vector projection will be a vector. Okay, to see that in pictures, that might help. We have the following. So if these are vector maybe u, oops, sorry, we're doing v onto u. So let's say v, it's easier to see things this way, onto u. The vector projection of v onto u, by this drawing, to help us visualize what's going on, we drop this perpendicular line here. It's as if it's the shadow of v onto u in some sense. And we would draw in this vector here, and that vector would be the projection of v onto u. Okay, now its length, well, the magnitude of it is the scalar projection of v onto u. Okay, so that's the picture for the situation. Really, it's just a matter of calculations. For the scalar projection that we're asked to calculate for these two vectors, u and v, we're doing it for two-dimensional vectors in this problem. It works for three-dimensional as well. It's just fine, just have to calculate a third component in there for each vector. And we plug it in, u dot v over the magnitude of u, using the formula in the tan box, and we get a value that looks like this, 14 over root 17. For the vector projection, and that's what we expect, a scalar projection should result in a scalar. For the vector projection, we expect a vector to come out of this. So plugging in, writing down the formula as we have it, and well, u dot v, we've already found to be 14. Now this time we're going to square the magnitude of u on the bottom, so that root 17 will become just 17 from squaring it. And we multiply that scalar times the vector u. That's this component right here. When we're done with that, our vector looks something like this. Okay. And that's it, vector and scalar projections for v onto u or any vector onto another. picture and a basic worked example. Okay. Now, one application before we're done with all of this. This is work. So calculating work done by a force moving an object or a weight a certain distance, or by a force being applied over a certain distance. We all recall work as being force times distance. Now for dealing with a vector force, F, and a vector distance, D, then we calculate scalar work. Notice that's vector dot vector, work comes out as a scalar. That's not shouldn't be a surprise for those of us who recall a Physics 1 course or Newtonian physics. All right, so another nice characterization of this comes from what we had before. This is essentially the formula we saw before. If we take the dot product of F and D as a force and distance vector, well, we know that the dot product of two vectors is equal to exactly this, where theta is the angle in between these two vectors. Okay, so now we have two different ways we could calculate work. It just depends on what information we have available to us as far as which formula we choose to use. All right, so let's look at the example that we're given. A tow truck's pulling a stalled car along the road. The chain makes an angle of pi/6 with the horizontal road, or a line horizontal to the road, and the tension along the chain is 1.5 kilonewtons. How much work is done by the truck pulling the car for 1 kilometer? Okay, so we've got our car and tow truck drawn below. They have egg-shaped wheels. That's practical. We've denoted that the force, or the tension, along this chain or connection point is 1.5 kilonewtons. That's just the shear force of it, right? So that's the magnitude of this force vector. We don't actually have the force vector written down. We could do that if we wanted to, but we don't really need to do that. We'll just set it up as is. We know that the angle formed by that chain in a horizontal line parallel, or a horizontal line, is pi/6. Okay, so now we've got theta. That's pretty useful. And then we know that the distance we're going to travel is 1 kilometer. So that really can be written down as D magnitude is equal to 1 kilometer. We've got everything we need to use this formula. So why not? Let's do it. Okay, now below, we've chosen this formula. So we'll carry it out. We know that these three values, and really this is just a matter of plugging things in. We'll do a little bit of adjustment because we want to make sure we end up in the right units, or units that at least make sense or are familiar. And what do we have? Work is 1.5 kilonewtons. The force vector times the force vector magnitude times the distance vector magnitude times the cosine of the angle between them. What we end up with it is a sort of an odd unit here. We have 1.5 times √3 kilonewton kilometers, or kilometers. All right, well, let's change kilonewtons and kilometers to newton meters, just because that's what work is normally in. That means there's going to be a factor of 1,000 to get rid of this K, and a factor of 1,000 to get rid of that K as well. We see both of those occurring right here. And that leaves us with newton meters. Right? Now, 1.5 times √3 times 1,000 times 1,000 newton meters. Plug this into a calculator. It is approximately equal to 2.599 times 10 to the 6 newton meters. That's 2.599 million newton meters, basically. So remember, we did round that. I think it's practical going to 3 decimal places. When in doubt, carry it a few places and use your approximate equal sign. So there's our dot product, its application. It's a pretty useful thing. It's pretty easy to learn. It's pretty easy to learn to use it for practical problems like perpendicularity and parallel. And we'll see it quite a bit as the semester moves on. So 10.4 will be the next video, and hopefully you'll see that soon and get to work on all these problems. Good luck.